Good morning, everyone. Welcome back. So, this is our last uh, meeting online because the next 2 weeks, the next two Saturday, we're going to have exams. Your third exam and then your final exam. Okay. So, we're going to finish chapter 18 and even chapter 19 today. And the coverage of the third exam is what? Chapter 17 and chapter 18. Okay, so just like to share to you my slide. Okay, so we started chapter 18 already last time. Okay, so we just go over this briefly. So we talk about the redox reaction, what the redox reaction is. So we say it's an electron transfer. Okay, it involves this what we call reduction oxidation reaction. So as you could remember, you were given this what we call acronym to help you in the redox reaction, right? The Leora and Geroa. So you have loss of electron, oxidation, and reducing agent, and then gain electrons, reduction, and then oxidizing agent. And we tell ourselves that we can only determine the redox reaction if we know the oxidation number. And we got what we call the problem, what we call the example last time. Okay, so the way that you're going to at least understand the concept here is you have to know how to assign the oxidation number, because only the change in the oxidation number will tell you where there is a redox reaction. So for this one, both of these are what? 0, because both of them are elements. So here, this becomes +2 and this becomes -2. So from this, you could say magnesium is the one that undergoes what? So based on this one, from 0, it becomes +2. So that means it lost electrons, so it undergo oxidation. And that is also served as your reducing agent. Now, oxygen, on the other hand, from 0, it becomes more negative. So that means it gains electron, and that's the one that undergo reduction. Okay, and since it undergo reduction, that is your oxidizing agent. So there's a lot of things that you can be asked here in terms of what is the reducing agent, what is the oxidizing agent, which one is oxidized, and which one is reduced. Okay, so if you are asked what the agent is, you have to put the whole material or the whole substance. But if you only ask which element is oxidized and reduced, so when you say which one is reduced, you could say oxygen is enough. But if you're asked what's the oxidizing agent, you have to make sure that it is O2. So that's the thing that you need to remember. Okay, so we have discussed example like this during the in-person class, so I want you to look at them. Okay, go over them, because there's one question that you have wherein you're going to balance the redox reaction in the exam. So we will start right away with the so-called galvanic cell. Okay, so as at the beginning of this chapter, I mentioned that usually in the electrochemical process, there are two things that can happen. One, wherein there's an energy that is produced from a spontaneous reaction. And another one is you're going to use electrical energy to cause a non-spontaneous reaction to happen. So galvanic cell is one wherein you have a spontaneous reaction, okay, that produce energy. So if you have what we call a galvanic cell, these are the usual thing that you can see in a given galvanic cell. Okay, so you have an electrolytes, okay, wherein an electrode is dipped to them. So usually electrolytes is the ionic form of the electrode, which is the metal. Okay, so in a typical galvanic cell, you always have this metal that serves as your electrode that is dipped in a solution. Okay, so most of the time you have the metal electrode dipped in its ionic counterpart. Okay, but in some instances, when the species involved or the substance involved is not made up of metal, you still have there an auxiliary metal that serves as your electrode. Now, let's try to look at each of these metal. Okay, so what we have here is the zinc anode. And what we have here is the what we call copper cathode. So what are the things that we need to know here? Okay, so you need to know here what's the anode, and what's the cathode. Both of them are electrodes. Okay, now usually the anode is the electrode where oxidation takes place. So what happened during oxidation? There is usually the loss of electron. Okay, so you have to remember that the anode is where oxidation takes place. Now the cathode, on the other hand, that is where reduction takes place. So how are you going to remember the electrodes here? When I was a student like you, all I say is anode to oxidation, cathode to reduction. So vowel to vowel, and then consonant to consonant. Vowel is A, E, I, O, U, right? So anode is oxidation, cathode is reduction. And in the cathode, that's where you gain electron. Remember, when we have a redox reaction, it's just a gain and loss of the what we call electron. Okay, so the question that you can ask now is, how did you know, professor, that this is the anode and this is the cathode? There's a systematic ways of determining which is the anode and which is the cathode. Okay, and you will learn about it before the end of class. Okay, now what can we say here? Whatever that happens in the anode and whatever happens in the cathode, when we add them together, you have the so-called net reaction. Okay, so if you're going to look at the net reaction here, what is the one that is canceled out? Anyone? What is the one that is canceled out here?
The electrons.
Okay, you just cancel out the two electrons. So this one is just the result when you add this and this one. Okay, now let's see what's happening in each of the parts of this, what we call galvanic cell. Because who knows, you may be asked to draw a galvanic cell. Okay, now, if this is where oxidation takes place, so that means they lost electron, right? So if they lost electron, what is the charge that you have here?
Positive.
What we call the anode. So is it a positive or negative charge? Somebody said positive. Okay. Now, on the other hand here, since the electrons is being gained by the cathode, so what is the net charge that you have here?
Negative.
Okay. So that's a negative one. So if you're going to look at it, oh, this is becomes mostly positive and this becomes negative. However, that's not what happened. Okay. Because you have the so-called salt bridge. So what the salt bridge do, okay, is it tries to maintain electron neutrality. So what do you think is the function of the salt bridge? What does the salt bridge has? From the word itself, salt. And what does it do? It bridges the two electrodes. I think that's the simplest thing that you can do. Use the name itself, salt bridge, to describe its function and what it is. Now, as you could see, this is a negative charge, right? Because the electrons are gained here. So look at what the cation ion in the salt bridge. The cation ion in the salt bridge goes here. So if the positive charge goes here and this is a negative charge, so that means the electron neutrality is observed. Now, on the other hand, since this is a positive charge here, and you have what we call the chloride in the salt bridge going there, so positive and negative charge, the neutrality is also conserved. So there's no positive charge on this side and there's no negative side on this charge because the salt bridge tried to maintain, okay, both sides to be neutral. Okay. Now, if you're going to look at this, you could say this is what? A, B, C. This is the anode, this is the cathode, and the salt bridge. And in a galvanic cell, the electron could move A, B, C. No, it's not really, it's from A to C, not A, B, C. It is from the anode going to the cathode. Now, what other aspect that you need to know? So, usually if you have a galvanic cell, as I told you, that is your battery. Okay? And I would say that's one of the greatest contribution of chemistry to civilization. Okay? So I think because of this, what we call the contribution that you have here, this really what I could say light up the world. Imagine the 1800, okay? Electricity is not yet known. So Michael Faraday is trying to study about this one. So everything is being lighted up by what? Candles. Okay. Now the advent of this spontaneous reaction or the concept of the galvanic cell revolutionized the electric industry. Okay. Now, usually in the battery, you look at the so-called cell voltage, electromotive force, or cell potential. So that's the one that is produced. Okay. So if we're going to look at this, the reaction that we have in the previous battery, so this is what we have. And at standard condition, okay, the concentration of the solution that we have there is 1 molar. And a shortcut way of writing them is using this one. Okay, so you see here, it's really an ABC. This one, that's the salt bridge. And how do you end up looking at this? So all you need to do is to identify the anode, and then what's the one in the reactant side and what's the one in the product side for you to write this. And then for the cathode, what's the one on the reactant side and what's the one on the product side. Okay. So there's what we call the single line here that represent a phase boundary. So you have a solid electrode and a liquid electrolyte. You have a liquid electrolyte here and a solid electrode. Okay. So this is what or one thing that you should know, because either you're given this one or this one. But the thing is, if you're given this one, you have to write, you have to know how to write them in this form. Or if you're given this one, you have to represent them in this form. Okay? Now, let's go now to the one wherein, why did the zinc is the anode and the copper is the cathode, especially if we have a galvanic cell. Okay, so what's the basis? Okay, now if you have a problem that is a galvanic cell type, you have to follow the principle that we are going to discuss. But if a reaction is given, okay, so whatever happened here, the one that is oxidized is the anode and the one that is reduced is the cathode. Okay, so how did we determine that zinc is the anode and the copper is the cathode? So what they did before is to develop some sort of a standard rule wherein they determine the so-called reduction potential of each substance around the world. Okay, so what they do is they have the so-called standard reduction potential. So this is the voltage associated with a reduction reaction at an electrode when all solutes are 1 molar and all gases are 1 atmosphere. So this is where gases comes in. Okay, it's not all the electrolytes are solution. There are instances that they're gas. So what did they do? Okay, they have this so-called standard hydrogen electrode. Oops. So in the standard hydrogen electrode, you don't have a hydrogen metal, right? But what they do is you have this so-called platinum electrode that serves as the metal electrode. And then you have there an H2 gas at 1 atmosphere and a 1 molar HCl. And they look at the reduction potential of it as like that one. Okay. How do you write the what we call oxidation reaction for this? Anyone? Anyone? How do you write the reduction potential, the oxidation reaction for this? It's just the does that make sense? Can we say that this is the oxidation reaction for this reaction? Remember, from 0 it becomes +1. Here, from +1 it becomes 0. Okay? Now, what they did is they assign a corresponding value to this reduction reaction. To simplify it, they assign it as 0. Why? Why did you think they assign it as 0? Anyone? Why of all number is 0? Okay.
So that I guess if something is has more reduction power, it would be greater than 0, and those that are less than the hydrogen, it would be negative.
Okay, so the way that they assign it 0, because if the material has a higher reduction potential, it will be greater than 0. But if the material has lower reduction potential, then it is lower than 0. Okay, because if the potential has a greater, if the material has a greater reduction potential, what will happen? This reaction will become this. Because the reduction, if the reduction potential is greater than the one that you have here, then that means that material will be the one that is undergoing reduction. And the hydrogen that you have there, that's the one that undergo oxidation. And assigning the number 0 means that whatever the reaction, whether the reduction or oxidation form, the E will always be 0. Okay? So that's the way that they look at this, what we call standard reduction potential. So what do? Is they measure all metals against this standard hydrogen electrode, and they were able to get the reduction potential. So the first thing that you do is, let's say, okay, let's measure zinc against the SHE. And it gets a reading of 0.76. Okay? So if you're going to write the cell diagram for this one, this is what you get. Now the question is, which is the anode? What is the anode here? Conventionally, I want you to write your what we call galvanic cell in this form. The analyte on the right side and the cathode on the left. Oh, the analyte on the left side, the cathode on the right side. Okay, so remember, this is the anode, this is the salt bridge, and this is the cathode. Now look at the cathode. You have this, so this is the main reaction that is really happening. This one is just the electrode. Okay, so if you're going to look at the anode reaction, it's this, and the cathode reaction would look like this. And if we're going to look at the overall reaction, this is the overall reaction. Now, the question, how did they get this number 0.76? This is your so-called cell potential, the one that I have here, cell voltage or electromotive force. Okay, so how do you think they end up getting that number that come out there? So we can use this formula. Okay, so E cell, so this is equals to the cathode minus the anode. Okay, now between the two, which potential do we know? What does this information tells us? So between the two, we only know this one, right? And what's the value of this?
0.
0. We don't know this one. That's the one that we try to get. However, where does this value goes? That goes here. I think there's a number there. Okay. So from this, we should be able to get the value for this one. And what would that value be? 0.76, because we have what? A 0.76 equals to 0 minus the one that you're looking for. So the one that you're looking for that will be equals to so E, so you move that one that has what we call the 0.76 here. So that is equals to what? So that's how they get the reduction potential of your zinc. So what does this mean? So if you have a reaction like this, that is just equals to negative 0.76. You don't need to memorize that. That will be given to you. Okay. Now let's go to the other one. Okay, this is the one that I tried to show them. Now, what happened if instead of zinc, they're going to pair your what we call standard hydrogen electrode with copper? And this is what they get. So what can we say about this one? So this is the overall cell notation. And if we're going to look specifically at the reaction, look what happened to the hydrogen. It is now the anode. Okay. So if we're going to look at the thing here, so what value can we get from this information that we have here? So this is what? 0.34, and this is 0. And this is what we're looking for. And this is equals to your and if we're going to look at them, we just cancel this out here. So this is the value that we get. Okay. Now, try to look at this. When copper is matched with your SHE serves as the anode. Okay. But when zinc is matched with your SHE, okay, your SHE serves as the cathode. So what is crucial here? You need to determine which one is happening in the cathode and which one is happening in the anode. That's the crucial thing for you to know. Okay, and the one that is going to be useful to you, not only in the exam next week, but in the final exam is this one. And you will be given this. This is the so-called reduction potential. So what information you can get here? So if you're going to look at the reaction here, what's the half reaction here? Anyone? All of them are what? What type of half reaction do you see here? All of them are?
Reduction.
Reduction. Okay. So what information can we get from here? So the information that we can get from here, these values here, this will be useful to tell us which one is oxidized and which one is reduced. Or to tell us which is the anode and which is the cathode. Is that clear? Okay. So the cell potential is for the reaction as written. Okay. Now the more positive the potential here, so let's say this EO here, that's the reduction potential, just to be specific. Okay. So each of these is for this reaction. Now the more positive the reduction potential, the greater the tendency for the substance to reduce. Now, all of these reactions are what we call reversible. Okay? And the sign of your reduction potential changes when the reaction is reversed. And this is the thing that you need to remember. Changing the stoichiometric coefficients of a half cell reaction that does not change the value of your cell potential. Okay? So before we go on this one, let's try to go back with the copper and the zinc. Okay? So let's compare the copper here, which is this one, a plus 0.34, and a zinc that is a negative 0.76. So if we have a galvanic cell, so we're going to have like this cell equals to the one wherein you have the cathode minus the anode. So what do? We have to determine between the copper and the zinc which is the cathode and which is the anode. So which is the cathode? Anyone? Hello?
Copper.
Okay. So the cathode is the copper. Why? Why copper? Just want to sure you understand the concept that I'm trying to do, because this is the main idea that you should know in the galvanic cell. Why copper?
The reduction potential for copper is greater than the reduction
Okay,
potential
because-
of the zinc.
Because the reduction potential is greater than zinc. So both of them are in the reduction form, right? Now the higher reduction potential will tell the other one, hey, you oxidize because I have a greater reduction power than you. So here you can just assign as it is the value that you have. So what is the cell potential for this?
Is it 1.1?
1.1. Now the question, do you get this? If I ask you to determine the cell and you're given two metals. Do you think you can answer the question now? I tried to simplify this by just saying, okay, use this formula, because there are other formulas and it can be confusing to you, but if you're going to use that and you understand it, the value that you get is still the same.
It's almost 10 o'clock, Matthew. We're leaving. Second and we are ready.
Okay? Because another way that they look at this is this one. Instead of cathode anode, what do? They put the one that is reduced and the one that is oxidized. Not minus, it's a plus. What do you think happened to the negative 0.76 value when it undergo oxidation? Anyone? If you reverse the reaction, what happened to the sign?
It switches.
It
It will be
switches.
positive.
So it becomes 0.76. So another way of getting the cell potential is this one plus this. But you have to be very careful. Okay? That's why I always, what we could tell my students to stick to this one. And what will happen? All you need to do is determine the cathode and the anode. Whatever the number that you have there, just put the number there. Because if you're going to use this one, you're going to get the same 1.1, right? So I would say just stick to this one. Because that may confuse you. Okay? So let's try. So predict what will happen if molecular bromine is added to a solution containing NaCl and NaI. Assume all species are in their standard states. Okay, so how are we going to solve that? We're going to write down all reduction form here. So we have Cl and then we get the reduction potential. Now, usually you don't need to memorize that, it is given to you, okay? Now, there are other information that you can get here, okay? I can ask you here, which is the strongest oxidizing agent. Okay, if you're going to look at the table, you can see here, see that arrow here? The higher the reduction potential, okay, the greater is the oxidizing agent, increasing order of oxidizing agent. And the lower the reduction potential, the increasing strength of the reducing agent. So I can ask you the question here, like which is the strongest OA? And then I could put Cl2, Br2, I2. And then I can also ask which is the strongest Ra. And then I can also put their Cl minus, Br minus, I minus. So those are the things that can be given in your what? Multiple choice question. Okay. So before we proceed here, let's try to answer this question. Which is the strongest oxidizing agent?
The I2.
So the answer there is this. Because, oh, I don't think so. The strongest oxidizing agent there will be this one. The one that has the highest reduction potential. Look at here. See that? Increasing strength of oxidizing agent. So what does it mean? The higher the reduction potential, the stronger the oxidizing agent. Now, how about this one? Which is the strongest Ra? Is it still Cl minus or I minus?
It would be the Cl minus.
Okay, so it will be the, is it the Cl minus or the I minus? Anyone? It's the I minus.
Using it, yeah, it's I minus.
Remember, if I'm going to write this here, this is the increasing OA, and this is the increasing Ra, because that's what it is in the table. Okay? Are you clear on that? If I'm going to ask you a question about this one, multiple choice question, can you assure me at 2 points there? Okay, now let's go to the question here. So you have here, predict what will happen if you have Br2 that is added to a solution that contains Cl minus and I minus. So all of these are in, let's say, one solution. So what will happen? So Br2 can what? Oxidize one of them, but not the other one. So what do you think the redox reaction that can take place here? Anyone? So if I'm going to put here the one that undergo reduction and the one that undergo oxidation, so I would say the reduction is Br2 plus 2 electrons, okay, producing 2Br minus. Now the question, which one is oxidized? The chloride or the iodide? So what is the basis that we will use to determine which one is oxidized and which one is reduced?
Do we
Anyone?
consider how strong they hold on to the electrons? Which one's more electronegative?
No,
Oh,
it's just the concept that we discussed. This one, the reduction potential. So between chloride and iodide, which one is going to be oxidized?
Iodide?
Okay, iodide. Very good. Why? You look at the value here. So what did I say? Okay, so this versus this. This is higher than this one. So the higher reduction potential will remain in the reduction form. The lower reduction potential will undergo oxidation. You cannot do it here between these two. Why? Because your bromine has lower reduction potential compared to the one that you have here in chloride. Okay? Because what will happen here is your iodide, okay, will undergo oxidation. So 2I minus producing I2 plus 2 electron. And if you're going to look at the overall reaction, you just cancel this one. Are we clear on this? Because the other reaction that we have here is this one. But the question is, will this happen spontaneously? Will this happen spontaneously? Because those are the possible two reactions that will happen, but one of them will happen spontaneously and one of them will not happen spontaneously. Now the question, will this reaction happen spontaneously? Will you have it like this? The answer is no, it will not happen. Why? Because the reduction potential of bromine is lower compared to that of the chlorine. But you can ask the question, will this reaction happen? Yes, but not spontaneously. Okay? So I'll try to clean up again. So I tried to clean up this thing again. So what we have here, so you have 3 species. So you have the Br2, I minus, and chloride minus. Now, for you to have which reaction will happen, you have to write all reduction reaction of the species that you contain there. And we write it like this, based on the reduction potential. Now, there are 2 possible reactions that will happen. One wherein you have this Br2 reacting with its electrode producing 2Br minus. And the other one is, let's say, I minus or 2I minus producing I2 plus 2 electron. And the other reaction that will happen could be this. Now the question, why is this the only 2 reactions that can happen? Anyone? Why is this the only 2 reactions that can happen? Because those are the species that are present in the solution. So the reaction should have your bromine on the reactant side and either the iodide or the chloride. Did you get it? Anyone?
So Professor, just so I understand, if it was chloride that was added and it was, let's say, sodium bromide, then chloride would be reacting
Yeah,
with,
because what happened here is this
Right.
one will dissociate to give you what? Na plus and Cl minus. And this one will give you Na
Na
plus and I
minus.
minus. So the one that we're looking for is just this species there.
right. So if we replace, for example, we added chloride to a salt bromine, then we would replace the bromine in your equation with chlorine.
Yeah,
Right.
but the thing is, we don't have NABR.
Yeah, just hypothetical if that was the case in the.
Yep.
Okay,
So-
thank you.
So what you need to know is, okay, what's the species that we have there? So you have the bromine and you have the iodide. And where can you find this? So you have this one here, and you have this one here, and you have this one here. So there's only 2 possible reactions for that. Either this one and this one. Now, in this case, only one is spontaneous and the other one is spontaneous. Okay? Why did I say only one is spontaneous? Because one of them has a higher reduction potential than the other. Remember, you have here what? 1.36, 1.07, and then 0.53. So in this case, that means this will tell this one to oxidize, but this cannot tell this one to oxidize. So the reaction that will happen spontaneously is this. Because bromine has a higher reduction potential than iodine. And as you could see here, this one and this one here, okay, they should be on the same side because they are the one that is present there. Now, this one will not happen spontaneously, but you can make it happen. So when you say you can make it happen, you have to apply energy. Okay? So this is the one that will happen. And you can determine the cell potential for that. What that be equal to? And we can get the cell potential for this if you want to also. Remember, E cell is equals to what? Cathode, E cathode minus E anode. So what do you get from this reaction? It's 1.07 minus 0.53. Here, if we want this to undergo, you will get what? 1.07 minus 1.36. So what is the answer that you get there?
At negative 0.29
Where?
on the right for the bromine and the chloride.
So the one that we have there, 1.07 minus 0.53. So this is what? 0.54?
That's 0.54.
And this one here is 1.07 minus 1.36. So that's a negative point. Now, the value in the cell potential tells you what kind of cell it is. Right now, we just focus on the positive one because a positive one that tells you that's a galvanic cell. And if you have a positive cell potential, that means you have a spontaneous reaction. Now, why did I say the other one does not happen? Because as you could look at the cell potential here, it's a what we call a negative value. So a negative value means you have an electrolytic cell. It can only happen if you supply that amount of energy. Okay? So let's try another one. So a galvanic cells consists of a magnesium electrode in 1 molar magnesium nitrate and a silver electrode in 1 molar silver nitrate. So calculate the standard cell potential. So what the thing that we need to determine here? We need to look at the reduction potential. So this is silver plus and this is magnesium plus. And then we can get the reduction potential. The table should be given to you. So you have the magnesium negative 2.37 and silver 80. So what we are asked here is just this. So how are you going to solve it? So which is the cathode and which is the anode? Silver is what? Reduce or oxidize? What happened to silver? Anyone? Hello?
Silver is reduced.
Okay, silver is the one that is reduced. So in that case, magnesium is the one that is going to be undergoing an oxidation. So if undergo oxidation, it will become like this, right?
Professor, can you go over why it's reduced again, please?
Because that's the one that has the higher reduction potential.
Okay, thanks.
Remember the rule that we have here? The one that has the higher reduction potential, that's the one that is reduced. The one that is a lower reduction potential, that's the one that is oxidized. So what's the value that we put here? 0.80 and negative 2.37. Giving you what?
It's a 3.17.
Now, I want you to look at the reduction potential there. What combination will give you the battery that has the highest potential? Anyone? What combination will give you the highest E cell? So it should be the one that's here and the one that's here. Look what it is.
Lithium fluoride.
Okay. You familiar with lithium fluoride? What's the battery that you use in your cell phone? Is it lithium based?
Yeah.
Because the combination that you have there, that's what, 2.87 minus 3.05. That's the highest that you can get.
So the E cell is 5.92.
Yep. So whatever the answer there, that's the E cell that you have. And that's the highest that you can get from the combination that is known. Okay. So question. This is one of the basic and I think the most important stuff that you need to know so far in the lecture that we have today. If you're given the reduction potential, you should be able to predict which one is reduced and which one is oxidized. Okay? So we discussed that if we have a galvanic cell, what is the cell potential value? It's usually what? Positive. And we say that it is spontaneous. It will happen on its own. Okay? Now, if we're going to look at the relationship of this spontaneity with the redox reaction, maybe we end up with getting this one. Delta G is equals to negative NFE cell. Okay? And if we want it to be in terms of a standard state, that's a delta G degree minus N times Fe raised to degree or standard state. So what's the difference between these two? Here, you follow that it should have a concentration of 1 molar or a gas that has a pressure of 1 atmosphere. Okay. So the difference between this one, this is a standard state. So the only one that is new to you here so far is the F, and it is given to you like this. Okay. Now, in the previous chapter, you know that delta G has also an equation that we call the rattling, wherein there's an RT, negative RT times ln of K. So this, you relate your Gibbs free energy with the K value. So what we're going to do now is we're going to relate the K with the cell potential. So rearranging them, you end up with this. So the cell potential, standard cell potential is equals to RT over NF times ln of K. Okay, and if you have that value, you can either memorize it in terms of this or this. So that's the thing that you need to know. And if we're going to summarize what we have so far, we can relate the cell potential with the delta G. What does the delta, what information we can get from delta G? Anyone? What information do we get from delta G? Anyone?
Whether the reaction is spontaneous or not.
If the delta G is negative, the reaction is spontaneous, right? If the delta G is positive, then the written reaction is non-spontaneous. I hope you know that. Okay. Now, in the delta G, we should also get the relationship of K. When we have a negative delta G, your K is what? More than 1, because the forward reaction is favored. Okay, if the delta G is positive, your K is less than 1. Okay, because the backward reaction is the one that is favored. This is not new to you. We discussed this in chapter 17. Now, the thing that we do here is we just adding the E cell. So from delta G to the cell potential, this is the formula that you need. From the delta G to the K, this is the formula that you need. And from delta K, from the K to the cell potential, this is the one that you need. So I would suggest this one is just simplified to this. I would suggest you have to learn them. Okay. Your exam on what we call Saturday, you only have 10 multiple choice questions and everything are all problems. Okay. Now, if we're going to summarize the one that I'm writing here, we can summarize it here. Okay. So if we're going to look at this one, the delta G that is negative, the K is more than 1, and then the cell potential there is positive. If the delta G is, we could say positive, the K is less than 1, the cell potential here is negative. Okay, so if you're going to look at the unit, usually this is what? In joules, and this is in volts. Okay, K has no unit, right? K is just a ratio of the products over the reactant. But if you're going to look at the unit that is discussed here, so this is a J, the joules is in the delta G because it's an energy, and the cell is in the what we call volt because that's the potential. Okay? And under this condition, this is what you observe. Now, let's try to go on calculation. So again, you have to remember this number or equation that you have. Okay, because based on the exam that I have graded so far, you mess up the equation, you mess up the question. Okay, so let's try to do this one. Now here, you have to follow which one is oxidized and which one is reduced based on the given equation, if the equation is given. Okay? Why? Because you can now have a cell potential that is negative. Remember this? So what's the difference between the two? This is a galvanic cell and this is an electrolytic cell. So which one is spontaneous between the two? Anyone?
Galvanic cell.
So this is the one that is spontaneous. This is the one that is non-spontaneous. So now, your reduction potential table is just the source of your reduction potential. It doesn't mean that since this is higher, this is the one that is oxidized, or what we call reduced. Okay, so the basis that you have now, which one is the what we call the oxidized, which one reduced, or which one is in the cathode, which one is the anode, is based on the given equation. So we have here, you are asked to calculate the equilibrium constant for the following reaction. So which equation are we going to use here? Most likely this one. Okay, equilibrium constant, or if we go before here, we can use either of the two. Which one do you want to use? Let's use the L and K because that's the one that's first. Okay, so E cell is equals to 0.0257 divided by N. So if we rearrange this one, how do we rearrange this? So we can put L and K on one side, and then that is equals to N times the E cell over you follow? Now, let's go with the E cell. So we will consistently make use of cathode minus anode. And what I'm going to give to you here is just the reduction potential of tin 2 plus and tin, and the reduction potential of copper 2 plus and copper plus. Now, the question now is which one is oxidized and which one is reduced in the given reaction? Everyone? Maybe I'll make a roll call so everyone will be what we call the prepared. Because what I observed, the one that always answers, the one that's always what we could do well. So which one is oxidized, tin or copper, based on the given reaction?
Copper.
Okay. So which one is oxidized, copper or what we call tin? So copper 2 plus and then copper plus.
The tin is oxidized. It's losing the electrons.
I think tin is the one that is oxidized, because if you're going to look at the oxidation number, it's from 0 going to +2. Do you agree on that? Virgo?
Yeah.
I'm going to call each one of, because this is our last meeting, so at least I will see, I'll catch you if you're still sleeping or not. So tin is oxidized, Virgo?
Yes, I agree.
Okay. Because remember, in the oxidation number, if we're going to assign here, so 0 here, +2 here, +2 here, and then +1 here. So lost electron, oxidation, right? How do you lose electron? It becomes more positive. So that is the one that is oxidized. So the one that is reduced is Angelina. So the one that is reduced is the Richider. So what's the one being reduced?
I don't know.
Copper.
Okay, the one that is being reduced is the copper. Okay, now let's go now on the reduction potential, because you might say, oh, professor, you said the one that is higher is the one that should be reduced. Yes, that's true if it's a galvanic cell. But in the equation that we're given here, the formula is the one given. So you determine which one is oxidized or reduced based on the given formula. Are we clear on that? So we base it on the given formula. That's why I didn't give the reduction potential yet. If I'm going to give you the reduction potential here, so where's the table? So you have the tin, which is is 2 and 0, right? Because there's a tin that's what we call +4 and +2. I'm trying to find.
It's a negative 0.14 underneath PB.
Okay, so that's 0.14 negative, and the copper 2 plus to copper plus, what it is?
The 0.34.
Nope, that's the
Oh,
copper
no.
2 plus 2 copper.
Oh, okay. You passed it.
Here, 0.15. Okay, so if we're going to look at here, so you have here a 0.15 and here a negative 0.14. Now, which one are we going to determine which one is the cathode and which one the anode? The answer is this one. So what's the cathode? What value of the cathode are we going to put? Anyone? I'm going to what we call those who are what we call Sumitra. What is the cathode here? Okay, Sumitra's not ready. Shaneka.
Copper.
Okay, so is it the copper here? Yes. Okay, so what's the value that we're going to get? I'm going to call the other one. Tyla. What's the value that we're going to use for the E cathode? Okay. And then the other one, since Tyla is not ready, Samantha. See? You don't participate. That's why when I grade the exam, it's really low score on you. Okay. So the value that we have here is 0.15. Because that's the one that you have here. Okay. Now it just happened that it is higher than this one. Okay. Then minus, since the tin is the one that is oxidized, so that's the one that's the anode. So you have the 0.14. So what do you get here?
0.29.
0.29. Okay. Now, what would be the value of the K? So, K din. Will the K be more than 1 or less than 1?
More than one?
Okay, it's more than 1. Very good. Okay, because you have a positive value here of your cell potential, so the forward reaction is favored. It is a spontaneous reaction. So the next thing that we're going to do now is, what is N? What is the N value? Because if we're going to look at the equation, so we are here now. So we have the 0.29, the 0.0257. So what is N? Mashari. What is N equals to?
N is like the number of moles, right?
Yep. So what it is?
Let's see. Is it 1?
Okay. 1. How about another one? I'm going to call another one. Max. What is N?
Is it 2?
Okay, 2. So someone will have to decide or tie the tie break. Yasim, what is N? How do we get the N? So if you're going to determine the number of N, you have to break this down. So you have tin producing tin for 2 plus 2 electrons, and then you have copper 2 plus and 1 electron producing copper plus. So as you could see there, there's 1 electron here, 2 electron here, so you put the 2 there, making N equals to what? 2. You see why it's 2? Anyone? You see why the N is equals to 2? Because you have 2 electrons on these sides and 2 electrons on the other side when you balance it, which gives you the overall reaction like that. Okay, do the operation. And I'm going to call you. So it's not always Tigran that will do the answer. Okay?
Okay, Professor. So the N is actually the number, so it would be the number of electrons, the number of moles of the electrons.
Yep. So the N is equals to the number of electrons when you balance them. Okay? So what is ln of K here so far? We do it step by step. So ln of K is equals to, Sumitra answers 22.57. So how do we remove ln to get the K?
It's E raised to that number.
Okay, so E raised to that number, which is 22.57. And what would be the number?
I got 1.58 times 10 to the negative 10.
Nope. That's a positive. So that should be what we could raise to the number. So you will get there around 6.39. That's what Sumitra said. Got?
Oh, yep. Mhm.
Around 6.4 times 10 to the
Negative,
Nine.
to 9.
Okay. You have to be careful, okay? So question. So let's have another one. But this time, what is the one being asked? Fatima, what's the one being asked? What's standard? What's standard free? What are they? How do we call them? What do you call that?
The delta G.
It's the delta G. Okay. So again, we're going to use here an equation. And that equation is this: delta G standard equals to NF times standard cell. Now, which one is reduced and which one is oxidized? So I'm going to make a roll call. So everyone will be able to have their chance or be awake. Jada, which one is reduced and which one is oxidized? Answer only one, because I'm going to give Nebana the other answer. So which one between gold and calcium is oxidized? And which one is reduced? Jada? Nirvana? Which one is reduced and which one is oxidized? Sabrina?
Okay. So gold will be oxidized.
Which one is oxidized? The gold?
Gold, AU.
Okay.
And Ca will be reduced.
Okay. So if we're going to look at the hot reaction here, so this is what? A calcium 2 plus 2 electron producing calcium. And you have here gold, okay, reacting with 3 electrons, producing Au3 plus. Oh, okay. Now, how do we balance this one to give us that reaction? Because we need to determine what is N, right? Because this is a delta G is equals to negative NF E cell. So if you're going to look at here, there's 2 here, there's 3, but since this is the one that is oxidized, we're going to rearrange it in this way, right? So this is the one that will react with that one. So what do we do here? We multiply everything by 3. So this becomes 6, this becomes 3. And this one you multiply by 2. So N is equals to what? Anyone? N is equals to 6. So in that case, we now have the value here of 6. The Faraday constant that is 96,000. If we're going to look at here, this will be given to you 96,500. Oops, 96,500. And then if we have the reduction potential, we have it here in terms of what we call gold, 150, and then calcium 287. That's 150, and then you have the calcium 2 plus and calcium that is negative 2.87. So how are we going to solve the cell potential here? Yep, the F is a Faraday constant. So the cell potential is equals to E cathode minus E anode. So if you're going to look at this, that's a negative 2.87 minus 1.50. And what is the E cell? Anyone?
Negative 4.37.
So you get there an E cell that is equals to negative 4.37. So if you have it there, so what is the Gibbs free energy?
It's 2.5 times 10 to the 6.
So that is how much?
2.5 times 10 to the
2.5
6.
times 10 to the
6.
joules per mole. The question.
For the reaction you wrote, gold plus 3 electron gives you gold 3 plus. Shouldn't it be the
No,
gold
I
3
mean,
plus?
the way that you do is you need to balance the electrons on both sides. Are you asking how we got the 6?
No. Okay, never mind. It's okay.
Your half reaction for gold, is it correct?
Yeah, you have to look at the one here on this side, the second one. See that? I transform it to what we call oxidation form.
Would the elemental gold react with 3 oxygens to give you gold 3 plus? Wouldn't it
No,
be
it's the
the
other
ion?
way. Look here. See that below it? I have an I reverse it. I have an 2 Au3 plus 2 Au plus 6 electron. Do you see it? I
So
underline
3
it now.
electrons.
Huh?
So
Do you
3
see it?
electrons are removed from silver to make it 3 plus.
No, I reverse the reaction. Okay, I'm not sure if you see it because so initially we have what? Calcium, right? And then initially what I wrote there is an Au plus 3 electron like that, but that should not be the case because this is the one that undergo oxidation. So I transform it to this. Do you follow me? So this one is not the one. This is the one that's the reduction. That's the one that's oxidation. Do you follow now? Hello? Are you there?
Yes.
Okay. So what will happen? So I have 2 electrons here. I have 3 electrons here. So I swap. So I multiply everything here by 3. So this becomes 6. This becomes 3. And I multiply everything here by 2. So you end up oh wait, I think I'm right already there. I think I messed up. So it has to be Au producing Au3 plus 3 electrons. I think that should be the right formula there. Okay.
Yes, that's what's
Yeah,
confusing
that's
because
Yeah, same here.
Okay, so this is the one here and this is the one here. So that's my mistake. So I think it clarifies everything now. So you have 3 calcium 2 plus 2 silver, not silver, gold producing 2 Au3 plus and 3 calcium. So I think this one clarifies everything, right?
Yes, thank you.
Okay. Because we need to go back on, what's that? Yeah, I think that's a mistake that I have here. This should be like this, and this is a 3 plus. I think I'm already like that one. Okay. Yep. At least it clarifies everything now. Okay. Now, before we have a break, I'm just going to give you the quiz in between this week and next week. 3 quizzes. And then in addition to that, I may give you some assignment that you need to write in the paper and submit before the exam. Okay? Is that clear?
Yes, Professor.
Now, I'm already telling you, okay? The quizzes that I gave is just between this and next week. So if you don't want to attend after saying that, it's up to you. Okay?
Professor, I have a question. So the assignment that you're going to give us, we should submit it via Blackboard or
No. I'm going to email it to you. You're going to print it out. You're going to solve it, and then you're going to submit it. Give it to me before the exam.
Sorry, I'm sorry, I didn't get it. So I give you the hard copy or the picture of it.
You print it, you answer it, hard copy. That's the one that I'm going
Oh, okay.
to get. And if ever you tell me
that makes
that you forgot it, then your grade will also be forgotten. It's as simple as that.
Okay, that makes sense. Thank you,
Okay.
Professor. Mhm.
There's a reason why I do it, and I would just say do it.
This is the form of extra credit.
Just do it. Okay.
Okay.
Because if I say it for extra credit, you're not going to do it. Just do it. If you don't do it, then it's fine. But all I can say is you will regret it if you don't do it. Okay?
And you will email us those, right?
Before we have question, yes?
You'll email us those, or they will be in
I will
Blackboard?
email it to you maybe Wednesday or Thursday. But the
Okay.
quizzes, there are 3 quizzes, 2 in
Mhm.
chapter 7 and 1 in chapter 18, 2 in chapter 17 and 1 in chapter what we call 18. I will open it when we're done. So we after this we will have a short break and then we will go on. Okay. And then I'll try to squeeze here chapter we could say 18. Oh no, chapter 19. The important part of chapter 19. Okay. So let's talk this and then we'll have a 10-minute break and then we will continue. So what happened if we vary the concentration? Because all the calculations that we have so far is what's the concentration? 1 molar. Okay. So if we're going to look at this, what we call the effect of concentration, we end up getting this equation. Okay. So the delta G that we have now is just dependent on the standard delta G plus RT, L, and Q. Okay. So I would like you to look at the difference here, the delta G and the standard delta G. So this is a standard condition. This is an other non-standard condition. Okay. So knowing the information that we have here, substituting this with this and this one with this, we end up having this equation. Okay. So Walter Nernst developed an equation on that. So what did he do here? He divided all of them by NF, negative NF. So what happened when you divide everything by a negative NF? So this one is canceled out. This one is canceled out. So you end up with this. Okay. Now, to simplify the thing that we have, this is just similar to what you have learned so far, but we just have what we call here the Q. So what is Q? Anyone? It's just the concentration of the products over the reactants. So what we're going to have here are questions wherein the concentration is different from 1 molar. Okay, but the calculation is still the same. So let's try to do it like this one. Predict whether the following reaction would proceed spontaneously as written. So you have cobalt plus Fe2 plus producing cobalt plus Fe. So what if the concentration that given cobalt 2 plus is 0.15 and Fe2 plus is 0.68? So how are we going to solve that? So again, we have to determine which one is reduced and which one is oxidized. So which one is reduced based on the equation? Anyone?
Fe2 plus is reduced.
Okay, so the one that is reduced is Fe2 plus. And the one that is oxidized is the cobalt. Okay, so what we're going to do, we go to the reduction potential table. Again, this will be given to you. So you have the Fe2 plus. So you can help me find it. And the cobalt. So I think the cobalt, I think I saw it, this one, negative 0.28, right? And the Fe is, not this one, Fe, what Fe is that? 2 plus? What is Fe?
Negative
0.44?
44.
Okay. So the equation that we will have there here is this. What is N? Anyone? What is N equals to?
So 2.
So N is equals to 2. Everyone agree on that? Okay.
Yeah.
So what is the cell potential? Because we're trying to get the thing here. So where will I put the negative 0.44? Or what value will I have in the cathode here? Based on the information here. So I get a 0.44 minus negative 0.28. Is that right?
I think so.
And that is equals to what?
Negative 0.16.
Now, how will I represent L and Q or Q? Based on the equation here. Can I say it's cobalt 2 plus over Fe2 plus? Does that make sense? Does that
Yes.
value make sense?
Yes.
Okay, because this is the products and this is the reactants. So if we're going to look at the value there, so this is 0.16 minus 0.0257 over N, and this is Ln of, I could put the N there as 2. So I have here, how do we do this? What will I put in the numerator? 0.15, and then you have 0.68. So what do you get? Anyone?
So negative 1.51.
Negative, I think Fatima got it's negative 0.14.
Yep, I got the same thing.
So what do you think happened? At the standard condition, it's still negative, right? And you change the concentration, there's a little bit of changes that happened there. Okay. This one, I would say this is, I think I'm going to give this as an assignment. Okay, because this is a challenging question. We will not have a question like this, but I might end up giving this to you as an assignment. So the last part that I'm going to give to you is we're already on the so-called effect of the concentration. Now, what happened if we have the same materials? Okay, or the so-called concentration cell, can we still get the battery? The answer there is yes, if they have different concentration. Okay. So example that I have here, let's say this condition here. I have this battery that is made up both of zinc. So one, that is what we call 0.1, and the other one that is 1.0. So the question, can we determine the R, or the what we call cell potential for that problem? Okay, so we're still going to use this one. Now, let's say if you're given just this problem in the exam, what do you think is the cell potential here? Can we say it's 0? Because it's made up of the same zinc. So whatever is the cathode, that's the same value as the anode, right? Does that make sense?
Yes.
Okay. Now what is N? So there's a 2 plus here, 2 plus here going to 0. So you could say N is equals to 2. Now the question is, if you're given that cell, what we call battery notation, battery cell notation. So where will I put the 1 and where will I put the 0.1? I think I still have a thing there, just to tell you where is the 0.1 and the 1. Okay, so where will I put the 1 and where will I put the 0.1? Since this one is in the product, so I put the 0.1 there. And since this is in the reactant, I put the 1 here. And what do I get? Do I get the battery? I just don't have, I have a hard time with my solar calculator. So what do you get? Anyone? Before we have our break? Is it a negative? I don't think it's a negative.
I got it as a negative as well.
Really? This
Yeah,
should give you a positive.
like the same
Oh,
value, but
you know,
negative.
no, I think I forgot because this is an E minus, right? There should be a negative on that. Remember, E equals to E minus 0.0257 to ln 0.1 over 1. So that is the one that is 0. So that means a negative.
Okay.
Okay. So it's a 0.0296, right?
Yes.
So we will have a break. We'll resume at 11. So we will finish chapter 18, the remaining, which is just electrolytic cell and electroanalysis. And then we proceed right away with nuclear chemistry, and whatever time we have, we use it for review, in case you need the review session. Okay? So see you by 11.
Professor, can you go back to one of the slides? Which one was it? Slide 18.3 or example 18.3? Thank you very much.
So the next slide that we have are the common batteries that we usually use in our everyday life. Okay. And you will see today what's the chemistry behind this battery. So here, the dry cell or Lackland cell, this is like a Duracell. So if you're going to look at the redox reaction that is happening there, so you have the zinc that is oxidized to zinc 2+, and in addition to that, in the cathode half reaction, you have ammonia reacting with manganese dioxide to produce manganese oxide, okay, and ammonia ion. So if you're going to look at the reaction, this is how it looks like. If I'm not mistaken, here you have a graphite cathode. If you see some black solid particles there in the sample. Now, for those who have okay, this is the mercury battery, but they seldom use this one because of the environmental danger that is brought by mercury. Okay, so you have the zinc with mercury reacting with hydroxide to produce zinc oxide and water, and then you have mercury oxide reacting with water to produce mercury. Because of it produces mercury, it's not really environmental friendly. Now, for those who have cars, okay, you have there your car battery. So if you're going to look what's happening there, this is just the reaction that you have there. Okay. So you have the lead reacting with lead oxide in acidic solution and sulfate, and then producing lead sulfate and water. Okay. And I think this is reversible, right? Sometimes when the battery is dead, what do you do? What do you do when the battery is dead? You jump start it, okay? So that the reaction will happen again. Now, the lithium battery that I mentioned to you, this is the reactions that you have. So this is the oxidation, and this is the reduction form. Now, they have this so-called fuel cell, okay, wherein you have a hydrogen and an oxygen there. So your hydrogen is in the anode, it produces water, and your oxygen is in the cathode, you produce hydroxide. That's why I'm not sure. I don't know if you heard about this so-called water based battery. So they said there are some cars that can be run by just water. Now, the science of that is against it. But if you can have a device where you can put water and it produces energy, then I'm all for it. Okay. But if you ever have that invention or device like that, make sure you have your full security, because you're going to kill the economy of some countries overnight. If you say, oh, I have invented a car that runs on water, right? Overnight, some countries that depends on oil will go bankrupt. Okay. So that's the thing about this water-based battery that they said, or water, a car that is run solely by water. Okay. Now, you can take into consideration the action of bacteria. They said this is the battery of the future. Okay, so if you're going to look at the reaction there, so you have there the acetate with water, carbon dioxide in one side, and then you have your oxygen, acidic H+ producing water. So this is the what we call oxidation reaction, and this is the reduction half reaction. Now, the only problem is you keep continuing producing what? CO2, We have a lot of CO2 already around the world. Okay. Now, another aspect that is related to redox is, we could say, the negative side. And this has something to do with corrosion. Okay. They said if you're able to invented something that will make your metal lifetime forever, then I think you're going to get rich. Because what's the problem with metal? Metal will always what? Corrode. Okay. So when we say corrosion, this is the term usually applied to the deterioration of metals by electrochemical process. And this is how the metal corrode. That's loud. Okay. So in the anode, what happened? This is your iron metal. It is oxidized to Fe2+, which can further be oxidized to Fe3+. Now in the cathode, the oxygen, which is always present, so we say the oxidizing agent, and the presence of an acidic condition further what we call contribute to the corrosion of this what we call metal. Okay, and this is the explanation why Statue of Liberty is green. Originally it's supposed to be what? What's supposed to be the color of Statue of Liberty? Anyone?
Brown.
Okay, supposed to be brown because it's made up of copper. But because of oxidation, it becomes green. So the form of the copper that you have there, okay, is an oxidized form of the copper. Now, they have a way to what we call prolong the lifetime of what we call metal. So usually one thing that they do is the so-called cathodic protection. Or my term that I would use there is the sacrificial metal. And you can use this so-called reduction potential to it. Okay. So what happened? Let's say you have a lead storage tank or an iron storage tank. So what they do is they try to coat it with magnesium. So between magnesium and iron, okay, the one that would be first oxidized is your magnesium. Why? If you're going to go to the reduction potential, I'm just going to go back in the reduction potential just to show you everything placed around here. So if you have, let's say, magnesium, you have it here, and you have the iron. Not that one. I want the other iron. The Fe2+. So between the two, the one that will readily oxidize will be the magnesium because it has a lower reduction potential. Okay, so let's say if you have the oxygen, you have magnesium, and you have what we call the Fe. So the oxygen will act first on the magnesium and then the Fe2+. And the good thing about this, when the magnesium is oxidized, it forms a magnesium oxide that serves as a protective layer. Okay. The same thing that happens in our country where we use this Fe as what we call roofing materials. Okay. So what we do is we put it with zinc. Okay. So we call it GI, galvanized iron. So when you have this galvanized iron, the one that is being sacrificed or the one that is being oxidized first is the zinc. Okay, because zinc has a lower reduction potential, and the good thing, it will form a zinc oxide that serves as a protective layer of your iron metal. And it prolongs by 2 times the lifetime of that roofing materials. That's what happened in tropical countries. Okay, so that's a very good, we could say, application of the knowledge of electrochemical or electrochemistry. Now we go to the other end of the what we call electrochemistry. So what we discussed so far is this galvanic cell. So what happened if we use electricity for the reaction to take place, like electrolysis? So this is the process by which electrical energy is used to cause a non-spontaneous reaction, chemical reaction to occur. Okay, so for instance here, you can get Cl2 gas and Na metal from NaCl. Okay, so what you do, you have a battery there that supplies the energy for this reaction to take place. So your chloride is, what do you think here? Oxidized to chlorine. And then your Na plus is reduced to Na. As written, it cannot happen. But if you supply the energy coming from the battery, that reaction can take place. Okay? The same thing with the electrolysis of water. That's why I'm not convinced that you can have a car that can run solely by water, because by convention you need energy to break down water. You need energy to convert water to oxygen, that's oxidation, and you need energy, okay, to convert the H plus there to H2. Here, this is the electrolysis of water. And in both of these, you will collect oxygen on one side and hydrogen on the other side. Okay. So the anode here is here, and the cathode would be here. So if we're going to look at a problem of electrolysis, maybe we can look at this and see how we can incorporate the electrochemistry here. So for instance, here you have an aqueous sodium sulfate solution that is electrolyte using the apparatus below. Okay. If the products formed at the anode and the cathode are oxygen and hydrogen gas, respectively, describe the electrolysis in terms of the reactions. Okay. So what do we need to look at this one? So you have sodium sulfate. Now, you can ask yourself, the sodium sulfate hydrolyze? Does this hydrolyze? From your exam 3 topics, the sodium sulfate hydrolyze, yes or no?
Yes.
No.
No.
So if you're going to look at this comes from a strong base and this comes from strong acid. So both of them are from strong base and strong acid, so that means they don't hydrolyze. You only undergo hydrolysis if the conjugate acid is coming from a weak base and the conjugate base comes from a weak acid. But here, both of them are from strong acids and strong base. So what does this mean? Since they don't hydrolyze, okay, there's no Na plus and sulfate ion that is, we could say, available. Na plus will not be acted upon by the cathode, and SO4 2 minus will not act upon by the anode. So what do you have there? Which one participate in the electrolysis? So what's the other component that you have there? water. So the reaction that happened there is just like what we have discussed before. So you have water there that is oxidized to give you oxygen, 4H plus and 4 electrons. And then you have on the other side water plus 2 electrons producing H2 plus 2OH minus. So that's the reaction that takes place. So if you're going to look at this, what's the overall reaction here? If you're going to look at the overall reaction here, what will happen? I multiply this by 2, right? Because I have 4 electrons here, I only have 2 electrons here. So if that's the case, I will have 2 water here, and this becomes now 4 water. So this will become 6 water. Now the 4 electrons are canceled out. So this is 2H2 and this is 4OH. So if you're going to look at this, so you will have oxygen plus H2 plus how many water? 4. And if you break it down, you have 6 water here, 4 water here. So that means you eliminate the 4 water here, leaving you with 2 water. So 2 water will give you, there's a 2H2 there, oxygen plus 2H2. So that's the overall reaction. Your sodium sulfate will not hydrolyze, so they will not be undergoing reduction or oxidation. Now, the one that I want you to concentrate is this one, where the electrolysis is used for corresponding mass changes. Are you familiar with electroplating? Do you do soldering? If you are fond of electronics, okay? So there's a principle that is based on that, what we call technique, okay? So usually when you do electrolysis, you have to take into consideration the current that you apply times. So current, okay, and time, if you get the product of that, that will give you Q. Okay, and if you divide it by the Faraday constant, you will be able to get the number of moles of the electrons. And then you use the mole ratio in the half reaction to be able to determine the moles of the substance that is oxidized or reduced. And then you use the molar mass or ideal gas equation to get the grams of products or the liters of the product. So this is the one that we're going to look on. And there's a question of it in your exam next week. So you have a charge that is equals to the current times time. And then you have the so-called Faraday constant. So the Faraday constants, that's the charge that you have, okay, in 1 mole of electron. Okay, so the application for this is, I'm not sure if you're familiar with the dental filling, one of the worst experience that you can have based on my personal experience. So the way that they do it there is just they fill some of your teeth there with tin and mercury. Some would use tin and silver. Okay. So mercury and silver, like the one that you have here, or do you have the tin and the silver with tin? So let's try to work on an electrolysis problem. So you have here a current of 1.26 ampere passed through an electric cell containing a dilute acid solution for 7.44 hours. Now you write the half cell reaction and calculate the volume of the gas generated at STP. Okay. So how are we going to look at this one? Dilute sulfuric acid. And if we're going to look at this is just similar to our previous concept problem, H2SO4, wherein you have an H plus and SO4. So if you're going to look at this, it's just water that participate in the reaction. So you have 2H2O of water producing oxygen plus 4H plus 4 electrons. And then you have the other one, 4H plus. Oops, we're not done yet. Okay. Oh no, 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 no. I have to go back. I have to go back. Sorry for that. Share. So you have an H plus there that's coming from your acid, and it will react with an electron to produce H2. So what do we do here? If this is the half reaction, so this is the oxidation, this is the reduction. So we multiply this by 4. So you end up with 2H2O producing oxygen and 2H2O, 2H2. So if you're going to look at this is canceled, and you end up with that one. Now, how are we going to solve the problem? What we solved so far is just the half cell reaction. Okay. So based on this previous slide, we have current times time, right? So from current times time, or I just say ampere times time, you go to the charge. And then from that, you go to the moles of the electron. And then from that, you go to the moles of oxygen. Okay. So moles of oxygen and moles of hydrogen, because both of gases are produced. So we start with what? 1.26 ampere. You familiar? First time for you to hear the word ampere. And then 7.44 hours, which you convert to, for every 1 hour you have how many seconds? Anyone? 60 times 60.
3,600.
3,600. And then the way that you're going to do that is for every 1 charge that you have there, that is really equals to 1 atmosphere per second. So you just, I'm just going to do this until the charge. Or I can just continue in, because for every 1 mole of electrons, I have 96,500 coulomb. So I end up here with the moles of the electron based on the current that you apply there. So how many moles of electrons that you get there? 1.26 times 7.4.
It's 0.350. 0.035. 0.35 moles.
Did you get that? 0.350.
Yes.
Okay. Now, once you get that, you're going to determine now the number of moles of the things that you have here. Now, the question is, how many electrons are involved for every, let's say, 1 mole of oxygen? Because if we're going to look at this, you start this as 0.350 moles of electron times the moles of oxygen and the moles of electron. And you're going to do that also to determine the moles of hydrogen to the moles of electron. How many electrons are involved? Let's say for every mole of oxygen.
4.
Okay, can I say 1 moles for every 4 moles based on this? And here I could say 2 moles because I have 2 moles there for every 4 moles. And then from that, I can determine the moles of hydrogen. So 0.350 divided by 4. So I have this value. Then 0.350 times 0.5, I have 0.175. And what will I do next to determine the volume? I go back to one thing that I should learn in Gen Chem 1. And then I just divide this by P on both sides. Remember, the condition is STP. So what does STP means?
Standard temperature pressure.
Yep. So I have that. And then I have the 0.0821 liter atmosphere K mole. And then I multiply it with the standard temperature, which is around 273 K. And then divide it with standard pressure, which is 1 atmosphere. So you do the same thing there. So what is the volume of the oxygen and the volume of the hydrogen?
It's 1.96 for the oxygen.
Okay, so 1.96 liter. And for the other one,
3.92.
3.92. And this is the coverage of your exam next week. This is where the exam ends next week.
How soon will the PowerPoint be available online, Professor?
The PowerPoint are available online.
And I'm sorry, not the PowerPoint, your lecture.
Yeah, I mean, this will be made available after we're done. Right. So that's the coverage of your what we call the fourth exam. So what I'm going to do, because I prefer to do the chapter 19 today because we can record it compared to we do it in person. Okay. So maybe what we can do after the exam is just like a review for the final exam. Just to let you know, our final exam is also on a Saturday. I think it's 10 to 11:50. The December 18. Yep. So the next 2 weeks with me will be both exam. And then after that, we're done. So I don't know where are you in your Alex. But before we talk about that, let's go on with the chapter 19. The main reason why I want to do the chapter 19 is because we could say record them. And then we can still go over chapter 19 by next week. Okay? If ever you have some other clarification. So at least chapter 19 is not what we call as related with what we called before, although Korea or specifically North Korea always sell that they have this nuclear device, right? To the point that the former president, since he is observed with Kanye West, he got his own Kim with North Korea. Right? I don't know if you heard the news. One time, the former president says, oh, we fell in love with one another with the leader from North Korea, because North Korea's leader always says, we will nuke the US. Okay? So what we have discussed so far, what you have learned so far from Gen Chem 1 to Gen Chem 2 is all reactions happens in what? Outside the atom, specifically participated by the electron. Now, if you're going to look at nuclear chemistry, it's usually the study of the so-called nucleus of the atom. Okay? The study of reactions involving energies in atomic nuclei. And the history of the nuclear chemistry is a little bit, we could say, 100 plus years old. Okay, started when Antoine Becquerel discovered natural radioactivity, and it grew because of the Curie. Okay, so in most news you will know about the use of these nuclear armaments, right? What did they call the Russia, the mother of all nuclear bomb? I forgot the name at this time. Okay. So the way that we look at this one is all the nuclei would contain the different kinds of the fundamental particles. So what do you see in the nucleus? You can see the proton and neutron, right? So that's where what we call the nucleus is all about. And usually some nuclei are usually unstable, and that's the reason why they emit radioactivity. Right? So what do you need to know? The concept is still the same. Okay? It's still the same as what you have learned before. So you know about the atomic number and the mass number. Atomic number is just the number of protons in nucleus. Mass number is the number of the nucleons, the number of the protons plus the number of the neutrons. Okay, so that means if you're going to look at the nuclei, this is what you have. So this is the element, and this is the atomic number, and this is the mass number. And usually, if you're going to look at the mass number, that's the number of the proton plus the number of the neutrons. Okay. Now, the thing that you need to know is the terms that they use here in the nuclear chemistry. So you have the proton. A classic example of the proton is hydrogen. So a proton would only contain one proton. It doesn't have a neutron, just like your hydrogen isotope 1. Neutron, on the other hand, it doesn't have a proton. That's why the the atomic number is 0, but the mass number is 1 because you have one neutron. So this is the thing that you need to know for your final exam. Now you can have an electron which has a -1 atomic number, or the other term that they have to this is what? The beta particle. Okay, and then you have the positron. Positron is a positive electron. Okay, it's a shortcut of these two words. Positron. Okay, and last but not the least is the alpha particles. So the alpha particles, that's your helium. Okay, it has an atomic number of 2 and a mass number of 4. Now, why did I ask you to know them? Because in your final exam, you're going to do this so-called balancing nuclear reaction. And usually when you balance nuclear reaction, these subatomic particles are in bold. Okay. So one way to look at this balancing nuclear equation is make sure you conserve the mass number on both sides. Okay, like for instance there, uranium-235 reacting with the neutron to produce cesium, rubidium, and 2 neutron. Now look at the difference of the nuclear reaction. They change in terms of the identity of the element. It don't happen in what we call typical chemical equation. So that's one of the difference. Okay. Now in determining that you have the same mass number, make sure the sum of the protons plus neutrons in the product is equal to the sum of the protons and neutrons in the reactants. Another way to make sure that you balance the nuclear equation is the atomic number should be the same on both sides. So here, what did we look here at this instance? This one plus this one will give you 236. So that means you have to make sure this, and 2 times this will give you also 236. On this side, atomic numbers, so this one plus this will give you 92. And then this plus this will give you also 92. Okay, so let's try. Later on, we will try. Okay, no, let's try it now before we go with the difference of the nuclear and chemical equation. So what is missing here? I want everyone to participate. What is missing here? What is X here? So what's the difference here between the two? So 82 and 4 here, so that would be a 2. And 208 and 212 here, that's a 4. So what subatomic particle is that?
The alpha particle.
So you can do it like this or this one. Now how about this one? What is X? So as you consider 137, 137, so that's 0. And this one's 55 and 56, so that means this is a -1. So what subatomic particle has that?
Electron.
Okay, so if we're going to look at this, that is the electron or the beta particle. So those are the type of questions that will be asked, part of your final exam, not what we call the fourth exam next week. Okay. Now, if we're going to look at the difference between the chemical reaction and the nuclear reaction, you could see that there's a lot of difference. The one that you learn in terms of chemical reaction, the atoms are what? Rearranged depending on bond breaking and bond formation. But in the nuclear reactions, there's the element that is converted from one to another, from one form to another. Okay. So as you could see here, the element that you have here, you don't see it here. So there is a change in the identity of the element in nuclear reaction. In the chemical reaction, exclusively electron. But in the nuclear reaction, all subatomic particles can be involved. And then the chemical reaction, the amount of energy that you have is really low compared to the nuclear reaction, where the amount of energy is really tremendously big. That's the reason why they use it as a source of energy. And that's the reason why they use it as a weapon of mass destruction. Okay. Now, if the chemical reactions are affected by temperature, pressure, concentration, and catalyst, those stuff are not involved or don't affect in nuclear reaction. Okay. So the remaining portion that we have here is just like an FYI thing. Okay. So if they look at the nuclear stability, this is some of the summary that they're able to come up. Certain numbers of electrons and protons are extra stable. So what does it mean? Okay. Numbers like 2, 8, 20, 50, 82, and 126, they found it to be stable. Okay. And like the extra stable number of electrons, they're in the noble gas, the 2, 10, 18, 36, 54, 86. So these are when the noble gas are filled up. And then the nuclei with even numbers or both protons and neutrons are more stable than those with odd numbers of neutrons and protons. And what they observe, all isotopes of the element with atomic numbers higher than 83 are radioactive. And all isotopes of technetium and promethium are radioactive. So when you say radioactivity, this is the spontaneous, okay, emission of radiation in some of these what we call elements. Now, these are the numbers that they observe. So the thing that the main thing here is the even numbers, the one that gives you more stable isotopes. Add, there's only 4. Add proton and we could say even number of neutrons, there's 50. Even number of protons and odd number of neutrons, that's 53. But if you have an even number of protons and neutrons, that's 164. Okay. And here they have this so-called belt of stability. And what they found out here, as the number of protons increases, okay, the belt instability can be found higher when there's a 1-to-1 ratio of neutrons and protons. And based on this, what we call belt of stability, the one that is higher than the belt of stability, the one that is, we could say, usually observed, is the beta decay. When the ratio of neutron to proton is too large, the beta decay is the favorable mode of reaction. If its N to proton ratio is too small, it's the positron decay or the electron capture that is being what we call favored. And I want you to look at some of the reactions that they have here, because these are the types of questions that will come out like this. Maybe it's either this one is missing or this one is missing, right? If you have a beta decay, one of the particles that you have there that is produced is the beta particle. So what if the one that is missing is this one? Can you identify it? whatever the reagent that you have there or whatever the elements that you have there. Okay, so when you have a beta decay, what happens is you have a neutron breaking down to form a proton and a beta particle. Now, if you have a positron decay, the same thing. Okay, instead of a negative one, you produce a positive one. And the way that you're going to look at this, you swap this with this one. So one proton producing a neutron and a positron. This is the type of questions that you will be given in the final exam. So maybe the way that I do it is just, let's say I put this as X. Okay. So that's the one that you need to supply. You don't need to memorize this reaction. All you need to know is what's the proton, what's the electron or beta particle, and what's the neutron. And this is the alpha decay, the one that we have on that one. Now, the nuclear binding energy. You're familiar with this equation, right? Who developed this equation? Anyone?
Einstein.
Einstein. And do you know that this is the fundamental, we could say, explanation on the so-called nuclear energy? Based on the so-called nuclear binding energy, the energy required to break up a nucleus into components, protons and neutrons. So what does it mean? When your atom breaks down to its subatomic particle, they found out that it can be a source of energy. Okay? So you have here the so-called delta M. So that's what we call the mass defect. So I just going to discuss this to you, but I can assure you there's no question about this in the final exam. But at least for curiosity purposes, how Einstein predicted how you can harness a large vast amount of energy from the atom. This is the explanation that we have. He didn't win the Nobel Prize for this one. He's just known for this theory of relativity. He won the Nobel Prize for explaining the what we call photoelectric effect. So what is this so-called delta M? That's what we call the mass defect. Okay. So what does it mean? So the mass defect, look at the difference on the mass of the subatomic particle when you break them down, okay, compare with the given atomic mass. Okay, so for instance, the atomic mass of your fluorine is this. Now when you break them down, okay, so you have 9 proton, you multiply it with the mass of the proton, and then 10 neutron, you multiply it with the mass of this, what we call neutron. So you get the value of this. So there's a difference of that. And that is what we call the mass defect. And you can tap it as a source of energy. You multiply it with what C? Anyone? How do you define C? Speed of light. So if you multiply that using the conversion factor that you have there, you can get this amount of energy. Negative 2.37 times 10 to the negative 11. Very small, right? But remember, that's just in one atom. So for every 1 mole of atom, how many atoms do you have? You're going to use the Avogadro's number. So if you multiply that, that's the amount of energy that you get. Times 10 to the 13 joules. If you're going to look at our calculations, it's just times 10 to the 5 or times 10 to the 6. So the amount of energy that you can tap is really big. So this is the basis of the nuclear energy that we have. Okay. So the nuclear binding energy per nucleon versus mass number. So this is like the graph that they have. So the higher the nuclear binding energy over the nucleon, the more stable it is. Okay, so I'm not going to do this. And another thing that you need to know is the kinetics. Is this new to you? What chapter kinetics is involved? Anyone? Anyone? What
13.
chapter is energy kinetics involved?
Chapter 13.
It's chapter 13. Okay, so you're going to have a problem in your final exam that is kinetics. Okay, and the way that we're going to look at this one, what's order is this? Anyone? What is the order of that kinetics? So when we're talking about radioactive decay, we're talking about the first order. You still remember that? So the first order kinetics. So if you're going to remember, that would be KT in your chapter 13, but here we could say it as negative alpha T. Okay. So this is just similar or the same as the one that you have before, like that one. Okay. So if you're going to look at some of the kinetics, some of these radioactive materials, they can have longer timeline. Some are what we call shorter. So as you're going to look at your times 10 to the year, and then you have here days, minutes, times 10 to the 5 years, times 10 to the 4 years, and so on. So this is just the uranium decay series. Okay. Now, there are applications for this. You can use it for radiocarbon dating. If you want to determine some biological materials age, you can use that. Okay. I think number one applications for radiocarbon dating is in wine, right? The older the wine, the better it is. Now, if they want to look at the age of a certain materials, let's say some of the earth surfaces, they use this uranium-238 dating. Okay. Now they can also do nuclear transmutation. So in the nuclear transmutation that you have here, you just change them, okay, from one form to another. So I'm not going to do this. Just to show you the nuclear transmutation, most of the elements that we have are over 93, over atomic number 93, are usually a product of nuclear transmutation. Okay. So neptunium produced from uranium, plutonium produced from neptunium, americium produced from plutonium, the same thing with curium. Okay. Now, the thing that they have that comes in with the nuclear energy is either you have a nuclear fission or a nuclear fusion. So what's the difference between the two? Nuclear fission, you have a big material that is broken down to small materials like uranium-235. So uranium-235, okay, so it's hit here by a subatomic particle, okay, and then it's break down to give you strontium and xenon. Okay, so uranium-235 hit by a neutron, producing you strontium and xenon, strontium 90 and xenon 143, and 3 neutrons plus energy. Okay, so they look at the mass defect here, the equation by Einstein. So it's around what? 10 to the 11 per uranium-235 atom. Okay, so the amount that you have there is really what we call big. 1 ton of coal would only produce 5 times 10 to the 7 joules. In peaceful terms, you could say nuclear energy is efficient. The only problem of that is where you're going to throw the waste. Okay, so this is, we could say, the representative fission reaction that we have. So this amount that you have here, this is just the product that is produced. Okay, so the nuclear binding energy is uranium-235, strontium, and xenon. So these are the what we call corresponding nuclear binding energy. So in the fission, usually what you have here, you have a nuclear chain reaction. So this is a self-sustaining sequence of nuclear fission reactions. So for you to be able to meet the minimum mass of fissionable material required to generate a self-sustaining nuclear chain reaction, you have to have this so-called critical mass. That's the only way you produce your energy. Then I told you it's a very good source of energy, and unfortunately, the evil side of it is also a very good weapon of mass destruction. So this is what we call the uranium-235. They just put that some explosive to it. Okay. And then if you have a nuclear reactor, this is how it looks like. Refueling uranium 308. Now, the what we call most of the uranium natural uranium that you have here, which is uranium-238, okay, can be found on this what we call area, Oklo. So that is, we could say, the fission. The fusion, on the other hand, it's the other way around, small to big. Okay. So you have here deuterium producing tritium, and then deuterium reacting with tritium to produce helium. And then you have lithium reacting with hydrogen to produce helium. And each of them would produce a certain amount of energy. And this is per atom that is produced. Okay. So those are, we could say, the nuclear or the source of energy from nuclear resources. I told you they are, we could say, good. Unfortunately, the only problem is the waste product that you have, because it's longer. The half-life that you have for these waste products are much, much longer, 10 to the 9. So where are you going to dispose it? Okay. Now, for those who want to be doctors in the near future, there are radioactive base methods that they develop. It is radioactive base because they use radioactive material. Now, what can you say about the radioactive material that they use here? Most of the half-life are what? Short. If you want to do brain imaging or bone scanning, you can use fluorine 18. It has a half-life of 1.8 hours. If you want to monitor blood circulation, okay, they will ask you to drink sodium 24, and it has a 15 hours half-life. So the other stuff that you have here, as you could see, their half-life is what we call short. The first-hand experience we could have here is the thyroid activity. It's around 8 days, and they can see the difference in the thyroid. So for instance, this is the bone. So they can scan it by using technetium 99. Okay. So the way that they determine the amount of radioactivity, they use this so-called Geiger counter. So Geiger is a student of Ernest Rutherford. Okay. Now, whether you like it or not, every year we are exposed to radiation. Okay. And usually the amount of radiation that we have can be measured in terms of REM, the Röntgen equivalent for men. And these are the source of radiation that we have. So mostly from what? The X-ray. I don't know. Do you often take yourself, do you often have X-ray for yourself? Usually that is not advisable. Okay. But there are a lot of what we call applications of this radioactive material. Are you familiar with the Krebs cycle? Class? Are you familiar with it? They were able to determine the Krebs cycle by using the so-called radioactive, okay, material. So what they do is they have these radio-labeled materials and they monitor in every step of the cycle what form it is. Okay. And then in other scientific, what we call studies, they usually use the so-called radio-labeled compound. So when you say radio-labeled compound, they use either tritium or C14. And they try to monitor what is happening to that element in every cycle, and they will determine what's the structure of that element. Another thing that I have personal experience in using this, what we call radiation, is the problem of pests or infestation, right? What usually causes infestation? Usually insects. So in our country, we have problems with this. Are you familiar with mango? So every year, one province there, they always have problems with an insect that infect the mango industry. So what my advisor, we could say one of my old teacher did is they sterilize the insect. So what happened to that insect? Once it mate with other insect that's not sterile, that insect will become sterile. So after 2 to 3 years, the population of that insect that caused damage to the mango industry was gone. Okay, because what happened is they make all the insects sterile. So once they make, they cannot procreate anymore. It's just the same what they do with, I think in Florida, they make this genetically modified mosquito to eradicate the mosquito population that cause mosquito-borne diseases like the Zika virus and other stuff. Okay, they also use this radiation in food to eliminate these pathogenic bacteria. But the problem with this one is they just have to make sure that they what we call use low dosage, because at higher dosage the quality of the fruit is already what we call affected. So there is a good and bad sides applications of this what we call nuclear chemistry. It's up to you to what purpose you're going to use it. I told you it's a good source of energy, and the bad side aside of that, this is also a good weapon of mass destruction. So that's Gen Chem 2. Okay. So we're now ready for a review session. So this is already your fourth exam. So you already know what to do in what we call in the upcoming exam. And I already posted, I don't know if you knew it, I already posted the score for your third exam. Do you know it? I just didn't email you so not to what we call ruin your Thanksgiving break. But if you're going to look at it, it's already posted. Your third exam is already what we call posted. And the highest that we have in the third exam is a 96. So, question. Question? Class.
Are we going over the review for quiz 4 now?
Yeah, I mean, okay, I'm going to share to you. I already posted also some, what do you call this? If we go with the course material, where's that course material? So I don't know if you have noticed it. I already posted there. Chapter 17 problems. Why is chapter 18 not yet posted? I don't know. I think I can do it now. I know I did it already last time. So this is the recorded PowerPoint slide that we have. I know I did it already, so I think it's this one. Yeah. Okay, let's try to solve. Yeah. More electrochemistry problems there. And as I've told you, I'm going to open the quiz soon. Since I've submitted it already, I think I can open the quiz now. But I have to. When do you want it? Thursday night? So you don't do everything at the last minute? When do you want the deadline for these quizzes?
How about Wednesday?
Is Wednesday fine with everyone?
Thursday.
Yeah, can you please make it Thursday?
Okay,
Thursday.
Because I'm going to release to you by Thursday some assignment that you need to submit by the day of the exam. So I will open the other one. Also, all of them by Thursday.
It'll open Thursday morning.
No, I mean, it will be what we call the deadline will be a Thursday. Okay.
Oh, okay, that's fine. Thank you.
I still have.
So they're open now?
One of them is open now. Okay, until Thursday, and then by the end of the class today, I'm going to open the 17 and 18 quiz. So
Okay.
there's 3 quizzes that you need to do. Okay, and then the assignment that I'm going to send to you, it's by what we call email. So I will just attach there some problems. I would suggest do them. Okay. Now, for
Professor, I'm sorry. Those quizzes, they're about 15% of our grade, right?
That is, I think 10%, right?
Oh, I thought it's the whole recitation grade is the quiz.
But isn't the recitation only what? Is it 10%?
It says 15%, I believe so. If I'm not mistaken.
It depends on what's on the syllabus that we have. So whatever is posted in the syllabus, we follow the thing that we have there. I'm trying to open the thing now. Just wait. Come on, open. Yeah, recitation is 15%. So the idea that we have here, whoever get the highest there will get the 100 when we accumulate all of the quizzes. Or I'll try to make it what we call manageable for every. I mean, we could say if I can get the 10 highest score there, okay, then I'm going to get the 10 highest score for the quizzes, so that everyone will have a good chance to get a good score for this, what we call the recitation part. Okay. So this is what we have now. So the lecture is 40%. So the final exam is only 20. So that means you only have 45% to worry by the what we call last day of class. How's your Alex? Yeah, I was not I mean, we're not able to give you the chance to open them again. Okay. I tried, but failed. That's why I'm asking you, how is your Alex? Can you get at least a 70 out of 100 there? We might be, we have not decided yet on the what we call the 4 exam, but most likely it's cancel the lowest to the improvement of the class. That's I think the way it's going to be. Okay. All I can say is this. So let's say we have the reaction here, right? So the first thing that we're going to do is to assign the oxidation number. So you have here what? 0, 0, +2, -2. So following the Leora and the Geroa concept, so we could say magnesium is the one that undergo oxidation, right? So it undergo oxidation and then it loses electron. So in that case, that is also your reducing agent. Why is it the reducing agent? Because the one that is reduced is the oxygen. So reducing agent because it reduces the other species. Okay. So the reducing agent is usually the one that undergo oxidation. Now, oxygen is the one that is being reduced. So that's the one that gains electron. Now, once it gains electron, what happened? it's responsible for the oxidation of the other species. That's why you call it the oxidizing agent. Now, the only thing that you have to remember is if you have what we called here, so that's the one that is what we call reduced. But if you're asked what is the oxidation number, oxidation agent, oxidizing agent, you have to write O2 because it's the whole oxygens that is responsible for the oxidation of magnesium. So I think this is the thing that you need to remember.
Yeah. Okay. Thank you very
The
much.
one that is oxidized is responsible for the reduction of the other species, hence they're being called reducing agents. And once that is reduced, it's responsible for the oxidation of the other species. That's why it's the oxidizing agent.
Okay. Thank you.
Question? I have not seen the average for exam 3 because what I do is I just input all the scores. Okay. The chapter 18 problems are already up. I just put it there. It usually gives me an error. I'm not sure why. Yeah, so there's an error to it. I don't know why. So maybe I'll just email everyone that thing. Where's that? Because the last time I remember is I already what we called uploaded them, but it's gone again. So maybe I'll just email everyone the thing.
Yeah, it's not up yet.
So I'm just going to email this to you.
Thank you, Professor.
It should be up by last week together with the chapter 18. I don't know what happened. So it's called electrochemistry problems. So you see that, you hear that voice, so that's the one. The problem is it's usually a big file, but we'll see. Choose file. Okay, let's try this. Okay, it's attached now. So it might take a while for you to get it because it's a little bit big. I don't know how the Alex work because I tried to go to it. I'm going to try to see if I can. Because it doesn't give me specifics. Okay, so I'm going to show you how I see it. Then usually this is not how I get it. Usually the other faculty just posted it in a spread Excel sheet or sometimes in my what we call Blackboard. And that's how I end up getting the grades from it. So this is what I have so far with the you see the Alex thing here. So if we're going to look at the mastery here, so this is, I don't know what the 91% means, but at least some of your names are there. Okay. That's why if you ask me for specific there, that's all the things that I know. I cannot go uh, more specific than that, but I'm not sure if this is the grade that you will end up.
That's like out of the entire course, because right now my grade is higher than that. Maybe it's taking into account the stuff you haven't completed yet.
Yeah, maybe just the thing. Yeah, that's the thing. You might have a higher grade than this one, but this is not how I will get it. So usually what happened, there's just a spreadsheet that I get containing your grade about the Alex. But this is how I see them from my point. That's why I usually said I usually a hands-off policy on that one. So you might have a much higher grade than the one that is posted here. Okay. But usually I get it either during the time that we are inputting our final exam grades, or after we input the grades, and then I said, Kate, I need the grades now, and then it will be sent to me. That's why I usually put a hands-on experience on that. Okay, so any more question before we call it a week? So I would say start studying now. Okay, start studying not only for the fourth exam, but also for the final exam, because this is not the only course that you have. Okay, and I think you should know now the schedule of your other final exam because it was released already. So our final exam will be on December 18 from 10 o'clock to 11:50. So any more question? Before we call it a week? Yeah, same room. What room is that? 4M04?
So the class will start at 9 or
At 9:30. We're going to start the exam at 9:30. And I'm going to give you until 11 to finish it. Okay. Okay, if you don't have any more questions, see you next week. Study in the exam.
Thank you, Professor.